All right, hello. So in this lecture today, we are going to be looking at special orthogonal groups in 3 dimensions. And we are going to be speaking about its algebra, its generators, and so on and so forth, okay? So this is where we start off. And so, you know, the special orthogonal group in 3 dimensions, or SO3 as we call it, is similar to the group of rotations that we have in 2 dimensions, but the change, and it is a reasonably significant one, is that you go from being an abelian group, so rotations, as you know, as we have said, on a plane in 2 dimensions uh, commute, but when you are in 3 dimensions, Uh, the important difference with the 2 dimensions is that the rotations in 3 dimension no longer commute, right? So this is hence a non-abelian group. Okay, so this is a non-abelian group, and so that's the main point of difference between 2 and 3 dimensions. We will see more interesting things. And of course, some of this is going to be familiar to you from your, things that you've done earlier in life and so on. So now, rotations in 3 dimensions, as you know, they are going to be characterized by 3 specific angles. Now, this rotation, we can think about this as rotations around, principal axes of orthogonal coordinate systems. We call these coordinate systems x, y, and z. So around x, this is given as this you know r of x alpha is going to be given by this uh, coordinate. So you have fixed the x and you are rotating in the y and z direction. So this keeps x fixed. So this is, as you can understand, generalization of what you did from the last time around, saying that x primed is equal to x, but y primed is equal to y cos theta cos alpha plus z sine alpha, and z primed is going to be equal to minus y sine alpha plus z cos alpha. So this is a rotation where you have kept x fixed and you have done the rotation in x and y. So this is a rotation about the x-axis. Okay, very similar to that, you could also have something which is around the um, y-axis, and that is going to be r of y theta is given by similar things. Now the thing that stays the same is, of course, the y direction, and so that is what it is. Similarly, you can have another around the z-axis, right? So this is going to be given by r z phi. This is going to be something like this. Okay, now you are rotating around the z-axis, so keep this the same. One of the very simple things that you can do is you can try and look at, just to make sure that your angles, you are clear about the fact that your rotation on the 3-dimensional rotations don't commute. You can take these two, you can take rotations by 90 degrees, and you can impose them one after the other, and you will see that this r of x 90, r of y 90 is not equal to r of y 90, r of x 90. Okay, very good. So that's the bit about, oops, sorry, that's a bit about you know rotations in these particular directions. Now, what do we want to do? We want to actually find out, generators of these, these guys. So, like we did in the two-dimensional case, we can find these generators now. And so what we find is that you can look at A1, and this is going to be I del alpha of R of X alpha at alpha equal to 0. This gives you a matrix like this. Similarly, A2 gives you a matrix that looks like this, and A3 gives you a matrix that looks like that. Now, if you have done the, if you have got the Lie algebra bit of your mid-semester exams correct, then this should be starting to look very familiar to you. Okay. Now, what is this? This you can think of simply as the following. You can think of this as AI jk. So let's call this A1 jk. So this is equal to minus I epsilon I jk. Okay. This should be very, very clear. For example, you look at A1 jk, and that is given by the thing that you have out here. And it should be obvious that, this is A1, 2, 3. So this is 1, and that's the plus 1 that you have out here, okay? So that's very good. That's what this is saying. So this is, so what is this again? This is remarkably this is the adjoint representation of the SU2 algebra considered previously. So this is remarkable, and this sort of says that, since this is the adjoint representation, these guys follow this, it should be pretty obvious that the algebra of SO3 and the algebra of SU2 are one and the same, okay? That's a very profound statement that is actually true at the group level. That is actually true at the level of the algebra, and weirdly enough doesn't quite hold when you're looking at the groups. Okay, now let's look at this a little bit more. So what is our, if you wish, let's put this up. So R n cap of alpha should be just given by exponential of this generator. So it's I alpha n cap times a vector. That essentially means all the three A1, A2, and A3. So you can sort of write this as 1 plus sine alpha into minus I n cap a plus 1 minus cos alpha into minus I n cap a. Okay. All right, so this is the way I choose to write it. And so now what we can also do, we can also express our BC of theta as exponential of, so now this is, theta A into the epsilon ABC. We are doing this explicitly. So it's delta BC cos theta plus epsilon BCA theta gap A sine theta plus theta gap B theta gap C 1 minus cos theta. So this is just, expanding out the exponential. Should be pretty obvious what we have done here. Okay. So now what we want to do is that we want to figure out how this actually gives you the structure of the group manifold of SO3. What the expressions above do is that this gives you the 3D space with the angles theta A labeling these orthogonal coordinates. What we see from here, so okay, I should also mention that theta is sort of theta A, square root of theta A, theta A. What I should, yeah, so what I should, so this is sort of a three-dimensional space with the angles theta A that label its orthogonal axis. The group element is, you have to remember that the group element is the same for theta A and theta A plus 2 pi. So we have to limit the range of theta being from minus pi less than equal to theta less than pi. Okay, so this is something that we need to do. This what the construction is. So this sort of is the group manifold of SO3. Now this is so 3D space. So 3D space with angles theta A labeling orthogonal axis. Very good. And as I was saying, this is subject to this, right? This is a restriction. So what do we have? So we have so SO3 is essentially a group manifold, which is the inside of a sphere and its surface, and the radius of sphere is given by pi. And so this is, so what we have is you have theta squared is equal to theta 1 squared plus theta 2 squared plus theta 3 squared. This is this is the surface of the sphere, and minus pi has to be greater than or equal to theta greater than pi. So so this is a group manifold, if you wish. So group manifold of SO3 is the inside and the surface of the sphere where the radius is pi. Now, another point is that this is a little harder to see, perhaps, but the pi and minus pi represent the same element. So this would mean that there is an antipodal identification on the surface of the sphere of the three sphere. So this is called a real projective space. This is RP3. And this actually is not simply connected. Anyway, let's leave it at that. Now, what we see is that even though the algebras are the same, so the same Lie algebra can lead to different groups and different group manifolds where the topologies of the group manifolds are not the same. Okay. When a Lie algebra generates several groups, the one whose manifold is simply simply connected, as in this case SU2 is, in that case that particular group is called the universal so let me repeat that. If one of those sorry, let's get at this again. When you have a Lie algebra generated by when a Lie algebra generates several groups, one whose manifold is simply connected is called the universal covering group of these guys. Okay, so in this sense, SU2 is the universal covering group of SO3. This is more information right now than you would need, but this is good to know. Okay, so let me just quickly draw this. Yeah, it'll be there in your notes nevertheless, but let me just say this. So same algebra, same Lie algebra can lead to different groups and group manifolds. Okay, group manifolds with different topologies. As I briefly said and then rubbed out, this was something that was not simply connected. So and when a Lie algebra generates several groups, the one whose manifold is simply connected is called the universal covering group. Okay. And hence SU2 is the universal cover of SO3. As we will see, SU2 is actually is called double cover of SO3 because it actually covers it twice. So let's see that now. Okay. So let's call this. Let's see what we did here in my mind. So let's call this relating SU2 and SO3. Okay, and let's put a line here. Now let's do the following. Okay, so what we want to do is we want to consider the rotation of a vector in 3D Euclidean space. So X vector is X vector is x1, x2, x3. So that's a vector. And we take it to x primed with Rx. Or you can say, if you want a notation with indices, xa primed is RAB, xp. So this leaves norm of the vector invariant. Okay, norm of vector is invariant. That is summation over a x primed a squared is equal to summation over a xa squared. Now consider a 2 cross 2 Hermitian matrices constructed out of F. Constructed out of X. How do I do this? I call some X cap as X3, X1 minus IX2, X1 plus IX2 minus X3, such that X cap, dagger is equal to X. This is also the most general two-dimensional Hermitian matrix that you can write down. So there is a map between the vectors X and this 2 cross 2 Hermitian matrices X cap. Okay. Now the distance between the origin and X cap is given by the norm, the XA squared, right? Now, this is simply related. So a similar thing can also be, constructed from X hat. So X hat, so X cap, so X vector dot X vector. So the norm of X vector is related to minus of determinant of this X cap. This is something that you can easily see. So this is x1 squared plus x2 squared plus x3 squared, right? very simply. Okay. Now let's look at a general matrix of SU2. Okay. So A belongs to SU2. That's a U. Okay. SU2. And we define a linear map. This linear map is X cap goes to X cap primed is equal to A X cap A dagger. So if, as we have seen before, X cap is equal to X cap dagger, we'll also have X prime cap is equal to X prime cap dagger, right? Because yeah, it'll just rotate things across, and if you have two daggers on something, that just means this is A. So this should be clear, right? So this is just, so X primed dagger is what? So it's A X cap A dagger, the whole dagger. So that means that this is A dagger dagger X cap dagger A dagger. Now this is just A, this is X cap, and this is A dagger. So this is equal to X prime. Right? So one leads to the other. So if X cap is equal to X cap dagger, it'll also mean X prime, X cap prime is equal to X cap prime dagger. Very good. So yeah, we don't, this is of course straightforward. So where am I going with this? Now you also remember, so this actually defines a point. So this is going to define, so X prime is also going to define another point in Euclidean space. Now remember the other thing. So we need to determine what we need to see how the determinant is going to transform. So the determinant is going to transform as determinant of A X cap A dagger, right? And remember that, so this is determinant of A, determinant of X cap, determinant of A dagger. And remember that A belongs to SU2, so the determinants are all 1. So determinant of X prime is determinant of X. Okay, determinant of X prime cap is determinant of X cap. So this map also preserves the inner product, and therefore this defines, so map preserves inner product, and hence defines a rotation. Right? So now what we can do is we can take a matrix R belonging to, so take R belonging to SO3 like you had at first, and A belonging to SU2. For example, you can take rotations about x-axis. So in that case, what R is, we have done this before, of course. So it's 1, 0, 0, 0 cos theta, sine theta, 0 minus sine theta, cos theta. This equivalently translates into the following. This translates into an A. Now this is a 2 cross 2 matrix. So this is plus minus of cos theta over 2 I sine theta over 2 I sine theta over 2 cos theta over 2. If you do it about, so, and you can find the rest as well. So let me again just write this down. If you're going to be doing things about the y-axis, then again it's similar. R is, as you know, cos theta 0 sine theta 0 1 0 minus sine theta 0 cos theta. This is similarly given by A is equal to plus minus of cos theta over 2 sine theta over 2 minus sine theta over 2 cos theta over 2. And last but not the least, if you wanted to look at things about the z-axis, then R is again given by the stuff that you know. So cos theta sine theta minus sine theta cos theta 0 0 0 0 1. So this actually translates into A equals plus minus e to the I theta over 2 0 0 e to the minus I theta over 2. Very good. So the thing that you have to notice here is that for every element of R, there are actually two such things of SU2. Okay, so this is, so the relation that you get at the end of the day is that SO3 is actually SU2 modded by Z2. Okay, and SU2 is the double cover of SO3. It is the universal uh, universal covering group of SO3 for sure. But in addition to that, each element, you have two of these. So this is actually very significant in the sense that you will find that this is something that you're going to find in nature all the time. There's actually this factor of 2 of this rotation group. I mean, the fact that you have a theta here and you have a theta over 2 in the corresponding SU2 is going to mean something profound. So this would mean that when you are looking at, I mean, vectors, if you wish, and if you're looking at things that transform here, so if you're looking at, so what does this do? So when you have something and you come back, so you start at theta and come back. So when you do a rotation of 2 pi, the vector sort of comes back to itself, right? But if you do the same rotation of 2 pi out here, what is going to happen is that it's going to pick up a sign. So in order to come back, you have to actually do, go around it once more. And, you have to have a 4 pi rotation to get the same thing back. What is it in life that goes to itself with a minus sign if you rotate it by 2 pi? These are objects that you have learned about a lot. I mean, maybe not quite a lot so far, but you have certainly heard about them, and everything in the world is made out of them. So these are fermions. So fermions, which make up, fermions like electrons, which are all around you, uh, are things that actually transform under, when you're thinking about rotations, they actually transform not in the SO3 but in the SU2. Okay, we will. I'll try and give you a little bit more of this when we speak about the Lorentz group a little later. But this is something that you should actually actually pay attention to. A lot of physics, factors of two do not matter, but then there are some places where these factors of two become absolutely crucial. So this is one such place. Okay, this is one such place where a factor of two becomes extremely crucial. So you should take care of factors of two. So the overarching lesson from this part of the lecture is that you should really take care of factors of two. All right, so that's it for this class. We will, go again next time, and we'll have more interesting things to look at. But so far, that is it. So thank you, and see you soon.